Then let's have a look at the scheduling of threads. The scheduling means how can we make it such that one CPU can process multiple threads and make it seem as if they are all running together at the same time. And yeah, as I already mentioned shortly, that is not possible basically because a CPU can only do one thing at a time. So what happens is that the CPU switches between threads, and in such a way and so fast that we don't really notice that, and it seems as if all the threads are running together. That's what we call round-robin scheduling. You can see it here in this diagram in the bottom. So here is a situation where we have three threads, thread 1, 2, and 3, and they are executed one by one. So in the beginning, thread 1 is running for a while, let's say 1 or a few milliseconds, and then thread 1 is stopped temporarily. That is what we call preemption. It's not finished, it still has work to do, but it's stopped temporarily to give other threads a chance to also make some progress. So remember that term, that's called preemption. And when thread 1 is preempted, then thread 2 can run for the same amount of time. So that's again 1 or a few milliseconds. And when thread 2 is then preempted, then thread 3 can run for the same time. And when thread 3 is done, we again could go back to thread 1 because we assume there are no more threads. So then only thread 1, 2, and 3, they run for the same amount of time. And when that's done, we start again. That's the round robin principle. We start again with thread 1, again, same amount of time, then thread 2, then thread 3, and so on. Then again, 1, 2, 3, 1, 2, 3. So in this round robin way, all the threads are executed one by one. And when a thread is preempted, it just has to wait until it's again its turn. And every thread gets a turn regularly. In between two threads, you see there's a short amount of time in between two threads where the operating system runs. So the switching from thread 1 to thread 2, that is a bit of work. Some things have to be saved and some other things have to be restored. The work of thread 1, basically the values of the variables of thread 1, they have to be saved somewhere. And the values of the variables of thread 2, they have to be restored before thread 2 can continue. So this switching, that is meant with these kernel blocks. There's a short amount of time that the kernel, the RTOS itself, has to run, change some things in the processor, and then thread 2 can continue. That's the overhead that I mentioned. So here we have a little bit of overhead of the RTOS. The CPU cannot spend all its time executing threads, but in between two threads, each time there's a little bit of overhead of the kernel running there. Then every thread, and remember, FreeRTOS does not use the word thread, but they call it tasks. It has its own memory, its own set of variables. It's completely independent of each other. They can also share variables, but mostly it's independent of each other. So every thread has a thread control block, and every thread has a stack. And if you have more threads, then more of these thread control blocks and stacks are necessary. And they are all put in the heap. There is a memory area called the heap that contains these stacks and thread control blocks. And that's, as you can see, configurable. So you can configure the total heap size, and you can configure the minimal stack size. Every thread is always in a certain state. So for example, a thread can be running, like here in this interval, thread 1 is running, and here again, thread 1 is running, and in this interval, thread 2 is running, and here again, thread 2 is running, so then these threads are in the state running. But if they are not running, like here, thread 1, between this moment where it stopped and the moment that it starts again, then thread 1 is not running, because 2 and 3 are running. In that time, thread 1 is what we call ready. So running and ready means running actually now being executed on the CPU. Ready means it's waiting for its turn. And as soon as the CPU is free, it can become running. And yeah, as you see, a thread, this is a state transition diagram. A thread can go in between these states back and forth. So that's what happens here. Thread 1, now it's running in the beginning, and then for a while it's ready, while 2 and 3 are running, and then thread 1 is running again, and at the end of its time slice, it will become ready again to wait for its next turn. A thread can also be blocked. That's something else. That's not the same as ready. Blocked means that a thread is waiting for an external event. That can be a key press from a user. So it's just waiting for a value to come in from the UART port, or it can be a value from another device that's coming in. Some kind of event. You can easily imagine that sometimes we have to wait for events, especially in an embedded system. There are all kinds of events coming in from the outside, and waiting for such an event. That when a thread is waiting for such an event, then that thread is what we say blocked. So even if the CPU would be free, the thread would still not be able to continue because it has to wait for that external event. And that can be a button, again, that can be a button press from a user, it can be a key press that's coming in from a UART, it can be anything that's coming from outside of the embedded system and influences that thread. It can also be a timer, by the way, so we can also have a thread that's waiting for a timer. And then again, it's blocked and not ready. Ready means as soon as the CPU is free, the thread can continue its work. But if you are waiting for an external event, you need a value from a sensor, for example, before you can continue, then even if the CPU is free, the thread could not continue. So that's really a different state. Blocked is different from being ready. A thread goes into the blocked state always by calling some kind of API function. So you have a function like wait for timer, or wait for click, or wait for that input to go high, or whatever. So that's always a special call, an API call that is done before the thread goes into the blocked state. And that's always something that the thread does itself. So the thread itself decides, now I'm going to wait for some event. So it always is coming from the running state. In the running state, then the thread is doing things. And then it could be that the thread decides, now I'm going to wait. So the going to the blocked state is always coming from the running state. The thread must be doing that itself. And then how do we go back from the blocked state to the ready state? That's when that event occurs. So if you are waiting for a press on a button, then as soon as that button is pressed, then the thread will go from the blocked state to the ready state. And then as soon as the CPU is free, it can become running again. So mainly we have this sorry, we have this cycle here. So the thread itself decides, now I'm going to wait for something. When that something happens, then the thread will become ready, and as soon as the CPU is free, it will become running. That's blocked, and we have another state which is called suspended. That means that the thread is being suspended by itself or by another thread. So then it's not waiting for an external event, but it's just waiting until it's being released or resumed, as it is called here. That's also waiting, but not so much waiting for an external hardware event, but waiting for another thread to allow you to continue. So yeah, that is a separate state and also different from ready and different from blocked because it's not from an external event. When these threads are waiting, they are put in certain queues. So all the ready threads, they are in the ready queue. So here in this case, when thread 2 is running, for example, we have 1 and 3 who are ready. And when 3 is running, we have 1 and 2 who are ready. When 1 is running, we have 2 and 3 who are ready. So there are always a few ready processes, and they are put in the ready queue. And there's one running thread, which is here running on the processor. So the ready threads are in this queue. The running thread is on the processor currently. And then when a thread gets blocked, so it's waiting for some external event, then it's going to one of these other queues, depending on which event it is waiting for. There could be multiple threads waiting for the same event. So per event, you have a queue where all the threads waiting for that event are placed. So yeah, it's a different state and therefore a different queue, but yeah, basically one queue per event. I'm not sure if it's always implemented like that, but conceptually you could think about it like that. So you can have different events and you could have more than one thread waiting for that event, like a key press, and then they are put in that, all threads waiting for the same event are put in the same queue. Let's look at this example over here. Here we have 3 threads. They are called tasks because it's FreeRTOS. And they have different priorities. Task 1 has the highest priority. Task 2 has medium priority. And task 3 has low priority. The idle task, the fourth one that's shown here, that is a task that or a thread that will run only when there's nothing else to do. That's what an idle task does. So if there's no work at all, we still have to keep the CPU busy doing something. So then the idle task will run. And how this works is that the highest priority task, task 1, it's in the beginning, it's blocked. This arrow here shows how long it is blocked. That's until the moment that it starts here. We have the medium priority task that is running in the beginning and then blocked and then running and then blocked and then running. So it's periodic, as it says. And task 3, that's each time also waiting for an event with different times in between. So the arrow shows when it is blocked. And down here we see the idle task when that one is running. So since in the beginning task 1 and 3 are both blocked, only task 2 and idle task are left in the beginning. So because of that, task 2 will run at start because it has higher priority than the idle task. It has the lowest priority. So between time 1 and 2, task 2 is running. And then task 2 blocks itself. So it's going to wait for the next period. This is probably a timer that wakes up task 2. So at time t2, then task 2 decides to start waiting for the next timer event. So then all 3 tasks are blocked, 1, 2, and 3. So at that moment, the idle task will start running. Then at time 3, task 3 is unblocked, meaning the event that it was waiting for occurred. So then task 3 is going from the blocked state to the ready state. We can see that here. If the event occurs, then task 3 goes to the ready state. And since it has higher priority than the idle task, it also immediately goes through to the running state. So at time t3, immediately task 3 will start running. And 1 and 2 are still blocked, and the idle task has lower priority. Then at time t4, task 3 is again blocked. It's done reacting on that event that woke it up, and it's again blocked, waiting for the next event. So at time t4, we again have task 1, 2, and 3 blocked, and the idle task is then running because there's nothing else. At time t5, again an event for task 3 occurs, so task 3 wakes up, first goes to the ready state and then to the running state, blocking or preempting the idle task. That's now ready. But at time t6, that's a little bit later than t5, task 2 wakes up again because the event that it was waiting for, the timer, fired. That event occurred. So at time t6, also task 2 wakes up, meaning it goes from the blocked state to the ready state. Since it has a higher priority than task 3, it immediately also goes to the running state. So, and that also means that task 3 in that interval is ready. So it's not shown here, but in between T6 and T7, task 3 is ready. It's not blocked because it still did not finish what it was doing, but it's now ready because task 2 is running, and that's because task 2 has a higher priority. So between 6 and 7, task 2 is running. It did preempt task 3. Task 3 was not finished, but it still had to wait a while until T7. Then at time T7, task 2 is done, and it's going to wait for the next timer tick, timer event. So it's blocked. Task 2 blocks itself, and that means that task 3 can now run. There are only 2 tasks left, 3 in idle. 3 has higher priority, so then from time T7, task 3 can run until T8, and that's the moment that task 3 is done reacting on that event that occurs at T5. So then task 3 will again be blocked. And it will be blocked, we don't know exactly when, let's say somewhere between T9 and T10. So then again, we have 3 tasks blocked, 1, 2, and 3. So the idle task is running. Until task 2 wakes up again. Task 2 has a higher priority, of course, than the idle task, so it will take over the CPU. But it will not be allowed to finish its work as a reaction on that timer event on T9, because at time T10, then task 1 wakes up. The event that task 1 was waiting for occurs at time T10. So the moment that happens, task 1 wakes up and immediately takes over the CPU because it has the highest priority. So then we have T2 ready, but also T3 ready. T3 is being blocked until the end of the arrow here, somewhere between T9 and T10. Then the event occurs, so then it goes to the ready state, but it cannot run because there are higher priority tasks that are running. So T3 is being ready from the moment that its event occurred at the end of the arrow until T12. And between T10 and T11, task 1 is running and 2 is also ready. When task 1 is done, it's being blocked again. It's not shown here, but there should also be an arrow here at the end for task 1 being blocked. So at the end of the green line here at T11, task 1 is done, and it's blocked to wait for the next event. And at time T11, then task 2 will resume, because not resume, it will run again, because it was not finished yet also, until T12, then task 2 is done and it's going to wait for the next event. So that's the moment that task 3 can then run. But task 3 has been waiting, as I said, from the end of the error, the moment that its event occurred, until T12 has been ready all that time, but not able to run because of the task 1 and task 2. And at time T13, then task 3 is again blocked, and 2 and 1 also, so then the idle task will run again. So I hope you could follow this, otherwise look at it again. The idea is always that when there is a high priority task ready, so not blocked, not suspended, then it will immediately run on the CPU before any lower priority task. And it will even preempt a lower priority task. Like here, T2 between T9 and T12. T2 was running, but between T10 and T11 it was preempted by task 1 because it has a higher priority. And the same for task 3. It's running from T5 to T8, but in between T6 and T7 it's preempted because task 2 is then ready and running because it has a higher priority. Simple, actually. Always the ready task with the highest priority, that's the one that's running. And if there are multiple tasks with the same priority, then we have this round robin going on. So actually this round robin that we see here is only relevant and working like this when these threads have the same priority. If thread 1, 2, and 3, if they all have the same priority, then it will work like this. They get an amount of time and then they have to give the other two an opportunity to run. But if one of those 3 would have a higher priority, then that one would run always. There would be no round robin. A round robin is only between threads of equal priority. And between threads of different priority, like in this example, always the one that is ready and has the highest priority, that one will run. You have seen ISR's interrupt service routines earlier in this course embedded systems. Now we also have threads, so the question is how do these two interact and how do we make them work together? Well, first, how do threads and ISRs relate? Well, the fact is that even the lowest priority interrupt, it will always interrupt even the highest priority task. So an interrupt service routine always takes precedence over a thread task. And the task can also then, of course, not preempt an interrupt service routines. So threads will only run when there are no interrupt service routines running. If you don't want that, if you want your thread to run really without any interrupt, then you should disable interrupts. Otherwise, whenever there is an interrupt, it will stop the thread, it will preempt the thread, and then first execute before the thread can continue. So because of this, if you don't disable the interrupts, then you should keep an interrupt service routine always as short as possible. Shortest possible reaction on an external event. It usually has to be something like put a new value in a register or read a register or change the value of a variable, boolean, that so you can see that the interrupt has been there or something like that. But yeah, keep it as short as possible. And a thread is usually long. A thread is then meant for the longer work, and in FreeRTOS, a thread is actually never ending. It's a while statement that never ends. FreeRTOS cannot handle well a thread that stops. So the threads are meant for the longer running work. So how can we make them cooperate, as I mentioned? So let's consider the situation where we have an external device that delivers values to our device, like a sensor that gives us values, and that these values must be processed. So how could you implement that? Well, first of all, you could implement it completely without any threads. Yeah, only the main thread, only one thread. So the device, when it has a value, it generates an interrupt. The interrupt service routine then reads and processes the value. That is an option if processing does not take too long. Then you can do that. But yeah, as I said, the interrupt service routine should be kept as short as possible. But in certain situations, you don't need threads. You can do that with the things you already know, just the main thread and an interrupt service routine. You can also combine threads and interrupt service routine. So then the device still generates an interrupt for each value that it delivers. And then in the interrupt service routine, you do nothing else than read the value and put it somewhere in a variable. And then you wake up the thread to process the value. So then your interrupt service routine is short and the thread is doing the longer work processing the value. So that is an option. That's the second option. So yeah, then if you do this, then the thread, it will be woken up by the interrupt service routine. So the processing of the value will start as soon as possible after the value is available, after the interrupt has been given. And if that is important, that you react as soon as possible to a value coming available, then this is a good way to implement that. So in the interrupt service routine, you save the value somewhere that has been delivered, and you wake up the thread to process it. And then finally, we have the option to not use an interrupt service routine at all, do everything with threads. But then the reaction will not be as fast because then you will have the thread checking for new values regularly. There's no interrupt then. In this option, we don't use interrupt service routine, so there are no interrupts. But the only thing you can do then is make a thread that checks for new values every so many milliseconds or microseconds. And then when there is a value, read it and process it. This is an okay option if it doesn't matter that it takes a little bit of time between the value becoming available and the start of processing the value. So yeah, here in very short, you have the three options. Here you can do everything with interrupt service routines and not use multiple threads at all, only the main thread. You can combine threads and interrupt service routine. So the interrupt service routine is as short as possible, just stores the value in a variable or something like that and wakes up a thread then. Or the last one, do everything in threads, not use interrupts at all anymore. And depending on the circumstances, you can choose one of these options. Then let's go a bit more in detail, some specifics about threads in FreeRTOS and CMSIS. One important thing to realize is that in FreeRTOS, because that's our underlying operating system, threads are not supposed to end. So it's, yeah, you should not write threads that come to an end. The function that's executed by a thread, it should have some kind of never-ending while statement in it, so that it never reaches the end of its function. If you don't do that, if you let a thread end, then the behavior of the thread will become unpredictable. It's like a plane when it reaches the end of the landing strip. You might be lucky and the plane might still come to a standstill and everybody might survive, but it also might crash. And yeah, same here. If you are lucky and have a thread that ends, it goes well. The thread does not ruin the system, does not crash it, but it could also crash it. So just don't do that. And yeah, as I already mentioned, but I'm going to stress it again, the operating system FreeRTOS, it will always choose the thread with the highest priority to run, and lower priority threads only run when there are no more available higher priority threads, when all the higher priority threads are blocked. How is the scheduling implemented? Well, basically what we have is a timer that fires at regular moments, defining the length of the time that a thread can run uninterrupted. That's between 1 millisecond and 10 milliseconds. That order of magnitude you should think about. Whenever that timer fires, we have a so-called sysdig, which switches the threads. So it switches from one thread to another one, depending on the priority and depending on the round-robin order. All the threads, they get a turn, but only the threads with the highest priority. So that is done by the sysdig scheduler in the FreeRTOS system, and it's running every millisecond to 10 milliseconds. It's of course configurable. For very low power applications, you can also make a system that does not have these sticks, so it runs the thread until it stops by itself, or until it by itself gives the processor to another thread. But that's only in special circumstances, which we will not talk about. How to implement all this? Well, first of all, before you can do anything else, you must initialize the kernel, calling the function OS kernel initialize. Before you do that, you can hardly do anything. There are only two functions available before you initialize the kernel, and that's OS kernel get info and OS kernel get state. But yeah, only a few get functions, as you can see, but nothing really useful. So OS kernel initialize, if you want to start using the FreeRTOS kernel, it's one of the first things you will have to do. And then what you have to do is, in the end, start the kernel. So the kernel starts running, starts beginning the thread switching with this sysdig and switching from one thread to another when you call the function OS kernel start. So that must be, of course, after you initialize the kernel, but also after you created your threads. So you should create your threads, at least one, but often all the threads that you need, but at least one thread should be created before you call OS kernel start, because after OS kernel start, the thread switching will start working. Before you do OS kernel start, you can still, of course, call OS kernel get info, OS kernel get state, like before, and you can also create new objects. There are a number of these OS xxx new functions, OS thread new, but also OS mutex new or OS q new. There are a number of them. And you can call these before OS kernel start and after OS kernel initialize. Maybe you remember that earlier in this lecture I mentioned OS thread create instead of OS thread new. That was actually a mistake. OS thread create is from CMSIS version 1, and we are using version 2. This method, OS kernel start, once you have called it, it will not return. So whatever code you put after OS kernel start, it will not be executed unless there is some kind of error. But normally, in case of success, that function will not stop. It will not end. So we create a new thread by calling OS thread new. And what do you have to specify? Well, you have to specify a function that this thread is going to execute. That's the first parameter. You have to specify an argument for that function. So that makes it a bit more flexible. You can give that function an argument. And you have to specify some attributes where I will not go into now, like define the name of the thread and the memory it will use and the priority, of course, that the thread will have. So these are the three parameters for OS thread new. The function that the thread will execute, an argument for that function, and attributes of the thread, where the most important one actually is the priority. Because all FreeRTOS uses priorities, they are very important. Only the thread with the highest priority will run. Well, this is the place where you define the priority and the attributes when you do OS thread new. And it will return, if it works successfully, if it executes successfully, then OS thread new will return a pointer to the thread, actually a pointer to the thread identifier. When you call this before OS kernel start, then the thread is added to the thread list and it will start running when you do OS kernel start. When you call it after OS kernel start, so when it is called by another thread, when the scheduler is already running, then the thread will be added to the thread list and it will start running immediately. So you can call OS thread new also after starting the scheduler, after OS kernel start. But then it will have to be done by another thread, because all the code that you put after OS kernel start in your program, it will not be executed. So only the threads that you created, they will execute, and one of them could do another OS thread new. So the main flow in CMSIS version 2 using threads would be something like this. So you, of course, you have to include the right header file. You have to define a thread ID, which can have a name like task handle. Well, let's first go to the OS thread new here. So this is the place where you can create a new thread after initializing the kernel and before starting the kernel. There you can create a new thread. That thread is going to execute a certain function, in this case start task 01. So that function has to be defined before you can use it here, or at least declared before you can use it here. This function start task 01, it has an argument pointed to void here. That argument is given as the second argument of OS thread new. So when you start the thread, it will start executing this function start task 01, and it will use the argument arg. And you have to give the OS thread new some task attributes, and those are defined over here. So this is a name, a priority, and a stack size. That's are usually the least things you have to define. So this one has a normal priority, not high or low, but just normal priority. But you can choose, of course, any other priority. So this is all in the main function, as you see. The main function, of course, there will be much more in it, initializing a UART and all kinds of other things. But regarding the threads, what you have to do is initialize the kernel, create some threads, at least one, but there can be more, and then call OS kernel start. And you will never go past this. So whatever code you put down here, we will never get there. Often you see a while one, just to make sure, but you will never get there. So it doesn't really matter what you put there. So this is the basis about how to create a thread, how to start it. And yeah, just to repeat, you can call this OS thread new also from another thread. So in this function start task 01, for example, I could again call OS thread new to create an extra thread. But all threads, they are supposed to run forever. What we do need then is ways to communicate, to make tasks communicate and to make them synchronize with each other. And for that, we will we do have memory pools for shared data, message queues, semaphores, and mutexes. We will not cover them all. What we will look at are mutexes and message queues mainly. Well, let's have a look at how this all works in STM32Cube IDE. You see here that I have that IDE open. I have a project here called Threads, and let's start by looking at the CubeMX interface, which you see here. And regarding FreeRTOS, you have to go to middleware, and then here FreeRTOS. The pinout is of course not relevant for this. In FreeRTOS, you can choose which interface you want to use. CMSIS version 1 or 2 or none. And when you have made that choice, then down here you have a number of tabs where you can make all kinds of settings. So again, the API, but that's already set. The tick rate, so 1000 hertz, 1 millisecond per tick. So each time after 1 millisecond, a thread will be preempted and the next thread can run, and a number of other settings which we will not look at. And regarding the tasks, the threads, here you can add or delete threads to your program. So I can add one, it opens here. I can add a thread, my task 03. I can give it a certain priority. You have all the choices you can make for the priority. You can give it a certain stack size. You can define the function that it is supposed to execute. And a number of other settings that are usually not changed. Of course, you should choose more meaningful names than these, but I'm not going to do that now. I'm just going to click on OK, and then that task is now added to my list. There were already two of them. There was a default task, a thread test already, and now my task 03. So here we can see the list of all the threads that I just defined. By clicking on generate code here, the corresponding code will be generated. There was already some code which you can see now, but it's going to be updated. And then, as you know from past experiences, this main.c file, it's quite long, but let's see if we can recognize things. Here we have a thread ID, and there's one for each of the threads that I just defined. Default task, thread test, and my task 03. And what we also have is that for each of these threads we have the attributes containing at least the name, priority, and stack size. This is all about other things, but you also recognize here the declaration of the three functions. So I want for each thread. It's not the definition, it's only the declaration, and it's in the semicolon, so the definition is further down. Then we have to start with the main function, where we initialize a number of things, but this is the OS kernel initialize function for initializing our kernel. Here we have the definition of the creation of the three threads using OS thread nil. And there we have defined the function, the parameter of the function, none in this case, because all these functions that we had up here, they do have an argument pointed to void, but we don't use that. So then you can also specify null and the attributes. And after that, we have the OS kernel start. And as you know, that's where this program will end. So this while statement further down, it will not be executed. It's there for some kind of safety reason, but it will not be executed. So we should never get here, because now the scheduler takes over and it will schedule the 3 threads that we defined. So that now the 3 threads will run and not this program anymore. And further down, next to all the other initialization things, we have the 3 functions for the threads. This is what was generated by CubeMX. So we have to replace that, of course, by our own functions. But the default task is going to execute this code, a never-ending for statement, where each time it waits for 1 millisecond. Completely useless, but as I said, we have to replace this by our own code. And the second thread is going to do this, and the third thread is going to do this. You have to replace these 4 statements, but the important thing is that you must make your threads such that these functions never end. If a thread ends, you never know what will happen. It could go well, but it could also go wrong, so better just not make your threads end. So all the functions, all the threads functions that you define, they should somehow have a never-ending while or a never-ending for statement, like here. Well, let's make it a little bit more interesting then by replacing the code in those functions. As you can see here, I replaced the almost empty for statements by statements where something is printed through the UART port, the serial port, and every task is printing a different message. The first task is printing the message default task, the second one task 02, and the last one task 03. And I also changed the delay. Originally it was OS delay 1, but I replaced that by 1000 for the first thread, so that will wait 1 second and between printing the message default task. 2300 for the second task, so that will print every 2.3 seconds, and the last one will print every 2.9 seconds. This is already an example where the use of threads is making your life a lot easier. If you would have to make this in one while statement without using threads, so have one message printed every second, another message every 2.3 seconds, and another message every 2.9 seconds. Well, that would be possible, of course, but it would be more work than this. Here it's really simple. You just make 3 threads, and they each have their own frequency in which they print their messages. That's simple. In this way, it's considerably harder if you want to do that in one single while statement. Okay, then let's run this on the Nucleo. I have Putty over here. And as you can see, the 3 tasks are running. And we have the message default task every second, task 02 every 2.3 seconds, and task 03 every 2.9 seconds. And yeah, these are never-ending for statements, so this will run like this forever until we pull the plug or restart another program. So that is quite simple. I just defined these functions. Everything else was auto-generated. Here we have the attributes for the threads. And there might be one thing, if you look at the attributes more closely, that is surprising you. I hope there is one thing that is surprising you, because what we see if we look at the attributes of this of these three threads, we see that they have different priorities. The first one has a priority normal, and the other two have priority low. Remember what I said earlier, the threads, only the threads with the highest priority run. The ready threads with the highest priority run. But in this case, although the priorities are different, we see them running all three. Also task 2 and task 3, although they have low priority, which is lower than normal, of course, they are running. Yeah, I hope you can explain that. I will say it one more time. In FreeRTOS, always the ready threads with the highest priority are running, and all the lower priority threads have to wait for that. Well, why do we see them running here, all three? That is because of the delay. The default task, this one, has the highest priority. So basically it would always run, and the other two would not run at all. But in the code of this one is a delay, OS delay 1000. And OS delay 1000 means that this thread, it will wait for 1000 milliseconds at that point. So it will print the message. First it will print this message, default task. Well, that takes a few milliseconds, not much at all. And then it will wait here for 1000 milliseconds. And this waiting is blocked. So while it is waiting, this thread is blocked. It's not ready, it's blocked. So even if the CPU would be free, this thread would, for 1000 milliseconds, not use the CPU at all. So that is the reason that the other two threads also get a chance to run. And because the normal priority threads, the default task, which has the highest priority, and normal is higher than the two others which have low, it is not always using the CPU. It's using the CPU for a very short time and sending this message that takes a few milliseconds, maybe not even that much. And the majority of the time, this thread will be in the blocked state, not ready, but blocked, and therefore not competing for the CPU, and therefore the other lower priority threads also get a chance to run. If I would, for example, replace this OS delay, which blocks the thread, if I would replace that by a for statement, like this, so it's an empty for statement that only increases I from 0 up to a million. So the difference is that the thread will now be busy doing this for a while. And that is code being executed. So now I commented out the OS delay, so the thread will not get blocked anymore. But while it is waiting for the time to pass, it is actually doing things. It is increasing I continuously until it reaches a million. I'm not sure exactly how much time this will take, increase I from 0 to a million, but it will take some time. But during that time, the default task, the first thread, is busy. It will be doing something, so it will not release the CPU. If we run this, okay, it's now restarted. You see that now only the default task is running, because now continuously the default task is executing, and even while it is waiting, well, it's not really waiting, it's passing time, but during that passing time it is executing code, increasing I and continuously checking if it is smaller than a million or not. So now the other two threads don't have a chance to go in between. The first thread is continuously running. So that's a big difference. So this is what we call busy waiting. The CPU is busy while it is waiting in this task. When we use the OS delay, it's not busy waiting. It's blocked waiting. If we now would change the priority so that they are all the same, let's make them all normal. And start again. It's restarted, and now you see they are all three running again. The default task and task 2 and task 3, they are all running again. And because they now have equal priority, so while the default task is busy waiting, doing this, the other, it will be preempted, and the other two tasks will also get processor time. And then, as an example, to back up my statement that you should not make the threads end, they should stay in a never-ending while statement, infinite loop. Let's just make it end. So here I'm gonna let the first thread repeat only 10 times. So it will, 10 times it will print the message, wait a while. Not sure exactly how that was, but from the previous demo you could see it's also more or less a second. But now only 10 times, and then let's see what happens after that. So it's now just restarted. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And yeah, you see what happened after repeating 10 times. The first thread stopped. It just reached the end of the for statement, but somehow the other two threads also stopped. So yeah, basically the whole program crashed. To avoid that, it's better to let the thread stop itself when it is done. And you can do that by adding a statement like this at the end. So don't just let the function start default task in this case, don't let it just end, but when the thread is done, call the function os thread terminate. With that function, you can basically stop any thread. So once thread can stop another thread, terminate it. That's not a good idea. But you can also make the thread stop itself. And there's not really an objection to that. But in that case, you should give as a parameter, you should give the ID of the current thread. And you get it by calling os thread get ID. So with os thread terminate, you can terminate any thread, but it's not a good idea to terminate other threads. I'll go into that later. But the thread can also terminate itself and should terminate itself when it is done by calling os thread terminate and then with its own ID, which you get with os thread get ID. So if we run the program now, you will see that after the default task has finished, task 2 and 3 just continue normally. Here's the terminal. So now default task is still running 10 times. That's done by now, and then you see default task has stopped, but task 2 and 3 are still executing. So if you stop a thread, do it in a graceful way by using OS thread terminate.